Yet another database question. This time around, this question is based on the concept of simple pendulum and the time period of a simple pendulum. A very common experiment that we always conduct in our school. Generally, the simple pendulum experiment is conducted to determine the value of acceleration due to gravity experimentally. Now, as specified earlier, whenever there is an equation provided to us, remodify, adjust the variables here and there to ensure that it represents a straight line equation. Here we have a t is equal to 2 pi root over L upon G. Quite obvious, 2 and pi are constants, so is the value of a G. Therefore, this can be rewritten as t is equal to 2 pi under root G into root L. Now this very much represents the equation for a straight line. Y is equal to mx plus c. So if you plot a graph between time period along the y-axis and square root of L along the x-axis, I should end up getting a straight line whose gradient is given by 2 pi upon root G, and the y-intercept should in fact be equal to 0. So all of this I have already done even before going through or reading what the question is. Alright, so now let us check what the question is all about. It says, state for this experiment one variable that must be controlled. The one variable that must be controlled is obviously the value of acceleration due to gravity itself. So this experiment will be conducted at one location only. Now, apart from determining or having the value of a G as a constant, the other set of values that you might want to keep constant are, the mass of the bob. Mass of the bob that you are using, even though that is not specified in this particular equation, it is always a better idea to have the mass of the bob and the surface area of the bob constants, so that the air resistance and if any other factor are present and it might affect the value of the time period, might still remain constant. And the main source of error in T here is obviously, it says that the student operates a stopwatch to measure one oscillation and a millimeter ruler to measure the length of the pendulum. Isn't it quite obvious, when a student is trying to measure or determine the time taken for one single oscillation, there is going to be a huge error in terms of the reaction time. It is possible that you and me, when we conduct an experiment, we might start the stopwatch or put an end to that stopwatch not at the appropriate time. We might probably start the stopwatch a little late. We might also end the stopwatch a little late. So there is always a problem of the reaction time when we try to conduct the experiment and when we try to measure the time taken for one single oscillation. So it is always a better idea to take the time taken for around 10 oscillations or 15 oscillations, and then that time can then be divided by the total number of oscillations that have been counted. And that is what the next question here says. To determine T more precisely, the student measures the total time for 20 oscillations and divides by 20. And why do you think? Suggest why this is preferable to measuring the time for just one single oscillation. As already specified, if you are trying to measure one single oscillation, there could always be the factor of the reaction time featuring or creating a lot of error in your overall value. So it is always better to go for 20 oscillations. In fact, on a practical basis, when you actually try to conduct the experiment, it is preferable not to have 20 oscillations, because over a period of 20 oscillations, what happens is the amplitude of the oscillation might actually get damped. The oscillator or the bob might in fact not be able to travel to the original extreme position from where you actually started. To understand that in a better way, let me try to draw the diagram here. So this is your simple pendulum. Suppose you are letting the bob initially oscillate from this position. By the time we complete 20 oscillations, do you think the bob will be able to reach this point again for oscillation? There is always a possibility of damping, and hence the amplitude of oscillation might get affected. So it is preferable not to go for 20, but to limit ourselves, say, to 10 or 15 oscillations. All right, then it goes on to say that the student plots a graph with L on the horizontal axis. Achha, so here we actually worked it out considering root L to be along the x-axis. But then here he clearly mentions that length is being considered along the horizontal axis. In order to end up getting length along the x-axis, the entire equation here will have to be squared. So if I actually square this equation, I would end up getting t square is equal to 4 pi square upon g into L. This is also, in the form of a straight line equation. Y is equal to mx plus c, which goes on to say that, if I plot t square along the y-axis and length along the x-axis, I will end up getting a straight line. That is what he is asking. Obtain a line of best fit that is straight. As mentioned earlier, it is not necessary that the line of best fit is always a straight line of best fit. In order to obtain a straight line of best fit here, we will have to plot t squared versus L. So state the variable that must be plotted along the vertical axis. It should be t squared. Calculations using the data of the experiment show that G is equal to this value with a percentage uncertainty of 8%. Oh, there is a percentage uncertainty of 8%. Determine the value of G that can be obtained from this experiment. Include the absolute uncertainty in G to one significant figure. One significant figure obviously now brings down this value to G to be equal to 9.7 per second square. Now with regards to the absolute uncertainty, we already have the equation with us. Percentage uncertainty is equal to absolute uncertainty divided by the true value into 100, which indicates that the absolute uncertainty is equal to percentage uncertainty into true value upon 100. Percentage uncertainty is given to us as 8. So 8 into 9.7 divided by 100. Let's quickly try to determine this value here. It is 8 into 9.7 divided by 100 comes out to be 0.776. 0.776. We need to round this off to one significant figure, which means this can be expressed as 0.8, which means the value of a G is now being reported as 9.7 plus or minus 0.8 meter per second square. Hope you understood how to answer this question. Continue watching this space for the solution of more such database questions. Goodbye.